Good afternoon, everyone. Alex is here. Came with a new video. This one on how to use the online G renewal calculator to predict future recurrent events. And for the purpose of this video, I will demonstrate on homework problem 8.3. Just want to let you know, I am changing the numbers in this example, so do not reflect your homework solution on this video. First, let's look here and try to attribute the data. What are we looking at here? We're looking at 6 different systems, and I have a historic data for repair time or tune up time, as the problem calls it here. And I'm looking at 6 different systems, and the problem is asking you to predict the number of tune up in 3 years with 90% confident interval. Let's just imagine I have one system only. And I have historic data, and I came and asked you a simple question. How many repairs you had in 500 days? You would just go count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, you'll tell me it's 10 repairs in 500 days. But now I'm asking you for 3 years. So not only I'm asking based on historic data, I'm asking you to extrapolate, and I'm asking you to look at different systems. So you have to integrate all this system in one model, then use that model to predict the data that you're looking for. Let's see how we can do that. We're going to go to the GeoRenewal process. And it's asking you for 3 things as a start. Mission time, and I know that I'm looking for 3 years. Number of components, I have 6 different systems here. And input file with stored data. And that is the most important part of this problem. How to generate your stored data file properly. Let's go and look at that. As I mentioned, I changed the data, so you see it's different here. That thing to do that is a notepad file. And you can enter this data in 2 different ways. You can enter it vertically, you can enter it horizontally. Let's start with the horizontal. When you do horizontal, you can split or separate the failure times or the repair time using a space or using tab. I like to use tab. And it doesn't really matter, but it's just personal preferences. All right, I'm done with the first model. Now I would like to make a separation before I start to enter the new model data. 2 ways you can separate your data, either 0 or -1. We're going to talk about the difference between these 2 in a minute. All right, now let's enter the second model. You can hit tab and keep going, or my preferred way is to hit enter and start in a new line. The reason for that is this problem is only 6 models or 6 systems. In reality, you might have 100. So in one line, it's going to be confusing to track it. So separating it will be much better for me. And I will tell the system this is the end of model 2. I'm going to start model 3. Second way is the vertically, which is easy as just hitting enter. And at the end, -1, and I'm going to start the new system. Okay. Or I always say that a good engineer is a lazy engineer. Best way to do it with minimum effort. You can just add -1 at the end of each column or at the end of each model or system. And now, if you like to enter your data vertically, you just copy. You don't have to do anything because the -1 is already here for you. Here we go. If you like to do it horizontally, copy it all. Any empty cell, right click, paste with transpose. You see where is that? Paste with transpose. And copy this data and take it to a notepad, and it's right there for you. I'll stay with the vertical one. A really common mistake, especially if you don't do copy and paste like myself, if you enter your data key manually, some people forget the last -1, and that's going to cause a problem. Remember, when you did your inputs here, you told the software number of component is 6. Now the software is looking for 6 different separators. 1, 2, 3, 4, 5, and you forget the last one. So the system is now confused and it's going to give you an error. As a matter of fact, we're going to leave this data set without the last -1 just to see the error, and then we'll fix it later. But before we move from this point, let's talk about the difference between -1 and 0. Sometimes you would observe the model or the system for a certain number of days, let's say 700. And I'm going to make it yellow because that means it's suspension. It's when I stopped observing the system. Nothing happened, no repair happened at that time, no failure happened at that time. It's just a time where I stopped observing, similar to the sensor data in the unrepairable system. So when I do that, I have to tell the system or the software, the last data I'm entering is not a repair time, it's just observation time or suspension time. If that is a suspension time, you change your -1 to 0. So 0 is for suspension time, -1 is for actual repair time. Again, if that here is 500, and I decided to add that, then I have to change the -1 to a 0. But here there's some subjectivity, okay? Because I might tell myself, my last repair happened at 498. Do I really need to keep the 500? I might not want to keep it. So I'll just delete that and I'll be -1. Same here. Maybe this 700 means something. Maybe it was 720. And I want to like take credit for these 40 days. So maybe I'll keep it 720 and keep that 0. And by the way, when you input your data, you can have zeros and -1. It doesn't matter. It doesn't have to be all zeros or all -1. It can be mix and match. But we'll just keep everything actual repair time. I'll save my file. And now I'm going to go to the online calculator. Mission time. My mission time is 3 years, but I cannot enter 3 because my data file is in days. If I put 3, the software is going to think I'm asking for 3 days, but I'm asking for 3 years. So you have to convert it. Consistency is really important. Number of components, I have 6. My data file, I know it is not correct, but we're going to see the error. Upload, not enough numbers. So that tells you that your data file is missing something. We fixed it, go back, upload it again, and this time it goes through. All right, so from here, I have to enter some more data. The repair time. First, the distribution. We know it's viable. Viable distribution. Repair time. Repair time here is negligible, so we can put 0. However, I prefer to put a small minor value. I'm used to that because some Renewal calculators, you cannot just put 0 for repair time. So I put a really small value. And remember, this is 0.001 day. Like this is almost nothing. It's like minutes here. MLE and my Kijima models, there's 2 different models, 1 and 2, and we're going to talk about that in much more details at the end. But now let's talk about Q. This problem is as good as new. So that tells you 2 things here. First, this is an ordinary renewal process, ORP. Also, that means Q equals 0. So I'm going to go and put Q equals 0 and hit calculate. I get an error. it is telling me that the initial value for the restoration factor must be between 0.1 and 1. I mean, the software is limiting me. I cannot go down to 0. I cannot go below 0.1. And I believe this is some kind of way for how the software is written and how it iterates the data. But again, in reality, you would never see Q equals 0 because it's like you're rebuilding a machine to bring it back to the OEM condition. And that's not possible. There's wears, there's stairs, there's usage. There's a lot of stuff that you cannot escape. And this stuff is irreversible. I mean, imagine if you own a car for 5 years, no matter what you do, you would never be able to make it look like the original condition. As a matter of fact, you driving it by itself, the wind will faint the color and you cannot protect it from that. So again, Q equal 0.1 is actually a realistic and applicable number. And we're gonna see that in the mathematical model, by the way. Now I'm looking at restriction on Q. Here it is 1. And let's see what does that mean. I'm gonna refer back to lecture 7, slide 10. This is actually one of my favorite graphs in this class. Let's draw something right now, real quick. We're good as new, ORP. So technically I should go back to Q equals 0, but the software is not allowing me. It is allowing me to go back to Q equal 0.1, which is really, really close to Q equals 0. But the software, according to what I'm seeing, it's trying to look from a value from Q between 0.1 and 1. I don't want to go that far because if I went that far, I'm now going into the NHBB region. I want to stay here close to ORB, even though it's not 0, but I still want to close here or stay close here. So I'm going to enter a really small value close to 0.1. Let's say 0.11. So technically, I'm staying really close here. And I'm telling the software, look at only Q in this range. So like the software is restricting me, I'm restricting it too to look at a really small value of Q close to my ORB. I don't think this is relevant here, but for example, if you were looking at NHBB, I'll probably put 0.95 and 0.99. So now I'm forcing it to go in the other spectrum, but this is not what we're doing here. Confident level, I believe it was 90th. And we're gonna do two-sided. Hit calculate, then I get a really nice table. This table will forecast the number of repairs up to the mission time as specified, which is 1,095, 3 years. I can look at this data. 1 minute, I'll go to my boss and tell him, I'm expecting this system to be repaired 20.1 times in the next 3 years. And not in the next 3 years, in the first 3 years of the system age. Because again, I might be having data from a year prior. And I'm confident that this number will be between 18 and 22. Really easy. You just have to make sure you know how to do your data table. Really, really important. Before we jump into model 1 and 2, I want to talk about something extremely helpful to me personally, and I want to share it with all of you. Let's go here to the slide again. This is slide 11, lecture 7. It talks about the ordinary renewal process. And I remember when the professor was talking about it, he said that the MCF have 2 different terms. The first term is your CDF for the underlying distribution, which we call it TTFF, time to first failure. And it has a second term, which is a convoluted integral, which can be solved numerically. And again, as it says here, there's a closed form solution for the exponential, but we're dealing with Weibull. But the first half is what I'm really concerned about. This time to first failure is dominated by the underlying distribution. And based on this slide, I can use this information for my benefit. Remember, when we go back here, this is my time to first failure, all of those. Those are dictated by the underlying distribution, which is a Weibull. But then as you go down, you cannot use that distribution anymore because your distribution shift. And that's why it's a stochastic process, which that's the reason why we use Monte Carlo, right? So if I receive this data at my work, and again, I don't only have 6 models. If I'm talking about conveyors, I might have 600 conveyors. I have a lot of conveyors. So all of them come with time to first failure and then some other data that's dictated by a stochastic process. So before I even touch this problem, before I even go and solve it as a repairable system, I like to crunch it quickly to see what I'm dealing with. So I use half of the equation in slide 11, this one. I like to use that half because it's dictated by the underlying distribution. So if I took all those numbers, time to first failure, and took him to my friend here, Minitab, and solved it just like how we were solving the non-repairable component, I'll get the underlying distributions that dictates the time to first failure. That tells me what I'm dealing with before I even approach the problem as a repairable system. It tells me I'm dealing with a Weibull distribution with a shape parameter 3.4 and scale parameter 54.6. That should tell me a lot about the system, right? The beta is larger than 1 or less than 1, all this information that you know. But here is something really interesting I noticed. When you the models that we just solved using the G-Renewal, the second point, MLE method, it has a shape or a parameter, beta equals 3.4 and eta equals 54.6. That is exactly what I get from Minitab. So that tells me that this second line here has the parameter of the underlying distribution for the first time to failure only. Okay, this is something I wanted to share with you. Now let's look about model 1 and model 2. What's the difference between these two? I get a question from 2 students. And I again, guess where I'm going to go? I'm going to go to the lecture because everything in the slides. In slide 24, Professor Kijima slide. Here's the 2 Kijima model. It's Kijima 1 and Kijima 2 here, but this is model 1 and model. Actually, it's here right here, general repair model. Kijima 1 and Kijima 2. What are those two? Let's look at first. This one is described as Kijima 1, remove the damage incurred over preceding time interval. That means if I am at the 4th repair, I am repairing the system to go back to the original condition at the 3rd repair, not when the system was new. So I'm always going back to the last interval versus in the second model, it removed the damage incurred over the entire time interval. That means I'm going back to when the system was brand new. What is that? Let's talk about that in 2 separate ways. Intuitively, what does that mean? And then mathematically, what does that mean? Let's talk about intuitively. And I try to put that thing here for you to explain to you what is intuitively that mean. Model 1. Imagine I have a car, bought it brand new oil, engine, and I'm only focusing 2 aspects here. Obviously, there's much more, brakes and suspension, a lot of stuff, but I'm focusing on 2 things only, the oil and the engine mount. I'm driving the car, I got my engine mount loose. So I went to the first repair. I went to the mechanic and I asked him to fix it. So the first visit, he fixed the mount for me. Now I left, and maybe after 6 months, I need oil change. So I went to get the second repair, get my oil change. Remember, at that time, my engine mount is good because it was fixed here. Nothing happened to it. I left the mechanic shop here. 2 months down the road, the engine mount came loose again. But I didn't know. The vibration is not affecting me, and maybe it's not really loose. It's just not tight enough. I went to the mechanic for the 3rd time, for the 3rd repair, but I asked him to give me an oil change again. It's probably 6 months. Here, you will see the difference between the 2 models. If I'm dealing with just a mechanic that, all right, oil change, I'll get oil change, and he is basically trying to restore the oil change condition to where the last repair or last interval was, but he is not touching the engine mount. Maybe he doesn't even know about it, or he doesn't care. I don't know. So I try to restore the car's condition back to here, which is a second repair. Maybe I'll deal with a different mechanic, and now I'm talking about Model 2, okay? A different mechanic that is more competent. He fixed my oil change and he noticed that the mount is loose, so he tightened it. So he basically brought the car back to its original condition here. That is the difference between Model 1 and Model 2 intuitively. One is trying to go back to that previous interval, and one is trying to go back to the original interval. And here I'm finding an attentive student challenging me and say, well, in Model 1, you are going back to the previous interval. So interval 1 will go to interval 0, which is a brand new condition of the car. So 2 will go to 1, but we already said that 1 is the original condition of the car. So what's the difference? It should be always going back to that interval, but that interval is equal to the brand new condition of the car. I'm going to tell that student you are really attentive, and I get the same question when I first learn about these two models, but you would learn that this is true if Q equals 0. If I'm doing a perfect repair every time, but I'm not. Every time I'm doing repair, Q is not 0, Q is equal 0.1, so I'm going back a little bit worse than when it was. Again, let's go back to this slide. I'm going back a little bit before, and the time before I'm going a little bit before that, and so on. So I'm deviating from the 0 here. And that's in reality, again, your wear, tear, usage, this stuff is irreversible. And I'm going to show you that your question is valid once we go to the mathematical approach or mathematical explanation. You will see that that's possible if Q is equal 0, but Q is never equal 0. Now, before I leave that, I actually want to bring another example. And this example, Professor Vasily told it to me because I was struggling with it. It wasn't really easy to understand. He told me, imagine you have a sweater with a hoodie. And let's say that the hoodie can be unzipped from the sweaters. It can be separated. So today, I'm going to wash my hoodie only. And the next week, I'm going to wash the hoodie and the sweater. That means that the hoodie was washed twice versus the sweater was washed once. What does that mean? Let's jump to the mathematical model, and that would explain it to you. Mathematical model is relying on those three equations here and here. And you can see that, actually I have something put together to explain that. So for model 1, actually both first equations are similar in both models. A not equals 0 is the brand new condition of the car or the equipment. And A1 equal QX1, the repair effectiveness multiplied by the interval. Same here. The model started to change after A2, the second, third, fourth interval. You'll see from that model that Q is multiplied by the sum of the interval. So X1 and X2, Q is multiplied by those. But here, it has a different summation, and I have it set up here for you. If you look at model 1, and this is the algebra behind it, A1 is QX1, so if I substitute it here, I get QX1 plus QX2. I can take Q as a common factor, so I end up with X1 plus X2. When I do A3, the third time after restoration, Q is multiplied by X1, X2, X3. So I'm applying Q once, only one time. Now, when I go to model 2, we said it's the same first two equation. A2 equal Q A1 plus X2. If I substituted A1, which is QX1 here, I end up having Q square X1 plus QX2. Now, X1 get double effect from Q. Kind of like the hoodie. It was washed twice, but the sweater was washed once, right? This is the original summation, and I put it here because I'm going to go to A3 and A4 to show you the effect. I did all the summation here, and I end up with A3 equal X1 get triple Q, X2 get squared, and X3 get only one Q effect. If I went to A4, this is A4, copy and paste, right? A4, I get X1 now 4 effect of Q, X2 gets 3 times the effect of Q, X2 get Q squared 2 times, and X4 get once. Again, just like your hoodie. Go back here. I wash the hoodie twice, so it's getting 2Q. And I wash the sweater once, so it's getting 1Q. I have actually something else that probably would explain it to you. Here we go. All what I did here is I put different times, and this is the interval. 0 is the original condition, 1, 2 is the first, the second, the third, the fourth, and so on. So this is my number of repairs, the first repair, second repair, and I only put the equation from model 1 and model 2. Not a rocket science, I'm sure you can figure it out. But it's all based on Q. Now I'm gonna go to the attentive students that ask me the question and tell him, look what's gonna happen when I make Q equal 0. Every time I do a repair, the time goes back to its the time goes back to 0. So I'm doing a perfect repair. Every time I'm fixing it, I'm taking it back to original condition. But that is not reality. Q would never be 0 in reality. It's probably 0.1 here. So as I'm putting Q equal 0.1, you will see that there's a difference. Red here is model 1, and blue triangles is model 2. You will see how they are deviating away from the original condition, which is Q equals 0 or time equals 0. So you're deviating away, and model 1 is deviating away much faster than model 2 because we're not doing, again, the mechanic is just doing one thing and leaving another thing. So the system is going farther and farther from the original condition versus here, he's fixing the oil change, but he's touching other stuff to make the system better and more efficient and so on. So again, this is the difference between model 1 and model 2. I hope that explains it to you. If you have any further question, feel free to reach out via email, or I will see you in the office hours. You guys have a great day. Thank you very much. Bye-bye.